Okay. Sorry for that. Thank you for the invitation. I'm going to spend this half an hour, which you will realize maybe is much more than half an hour, trying to talk a bit about Credal models for uncertainty treatment. My first slide is a slide that was a joke 12 years ago. And the joke was that, maybe I can just read. Did you see the Cleverbot chart? Yeah, it's hilarious, but it's just clumsy and cannot keep chatting with you for a long time. So basically, the joke is computers can do many things, but it's still basic stuff like talking with you for a few moments. It can do. Okay, the joke ends up with attendees of Burning Man, but that part is less important for us. I think the important part is that 12 years ago that was a joke, and I think 5 minutes is not a problem anymore. I'm not claiming that computers are that good, but it's impressive how it's changed in these 12 years. And part of that is because of availability of data and computing power. So here's a graph just showing how quick the computers are getting faster, but also how cheaper they are getting. I will not try to explain the graphs in detail because that's the message of it. So computers, and especially computers for deep learning, have been very important for the growth of AI that we saw in the last 10 years. And this leads to things like this. So I did that. It took me an hour. I only use online tools. It's not amazing, but I took the face of the prime minister and I put on top of the face, that time was the health minister. This was during COVID period, and they were doing a press conference. And then we had two health ministers. Two prime ministers talking to each other because I overlaid the face of the prime minister. That's to show how easy it is with the techniques that are available. And there are other things and other concerns. So this is from this week, yesterday. So authors are suing companies doing AI because they are using their data without permission. And you see here on the left is the case of the author of Game of Thrones suing OpenAI. And on the right here, you have Google also being sued because a person died when it was given directions to go through a bridge that does not exist for about 10 years or so. I think 9 years or something like that. There was no bridge. It was during the night, and the car just fell, and the person died drowning in the water there. So it's clear to see that AI is affecting us, right? And more and more. And can we do something about that, right? So there are strong consequences. The research has grown very quickly and has had more impact in society. And AI may need stronger regulation because of that. We may need ways to certify how all the systems are working, and because we do not really understand them so well. Another approach that we're still not doing enough is to invest in better AI. But we should go there, and I think this workshop is pretty much in that spirit, in that direction of a better cycle of AI compared to our current one. And that is the second interesting cartoon of here. This is a hiring process where the AI is suggesting the most important quality of the candidate is to like the AI system that is evaluating the candidates. So I'll continue with some things that are happening now. So this is a week ago. So big tech companies met to discuss AI, and here's some sentences from Zuckerberg. So Congress should engage with AI to support innovation and safeguards. This one here is from Altman from OpenAI. I think this technology, if this technology goes wrong, it can go very wrong. We want to be vocal about that, and we want to work with the government to prevent that from happening. OpenAI are the folks behind ChatGPT, right? I think there should be a regulatory body established for overseeing AI to make sure that it does not present a danger to the public. That is Musk. And he continues saying that better that standard is set by American companies that can work with our government to shape models on important issues. I will leave you with that. I think it's enough and for you to take your own conclusions instead of me pushing any ideas, but I think my message is clear on concerns that exist at this moment. So to show some of the concerns in a more practical way or nice for us here, I start with the doctor's example. Maybe you have seen this before. I hope not, because then it's more fun. So patient Mr. Sick has either autoimmune or disease or infection, and if you know a little bit, you see the treatment for one kills you if you have the other, okay, most likely. And without treatment, you'll likely die. And let's say the diseases here are likely equally probable. Let's say that there are two doctors, and after studying the case in private meaning without talking with Mr. Sick, Dr. Imprecise tells she does not know whether it's A or B, and Dr. Precise tells that it's A. Which doctor would you prefer if you were Mr. Sick? Let's see hands here. So open hand is imprecise, closed hand is precise. Okay, that is a strange audience. I would say here that given this information so far, most audience would say Dr. Precise is a better doctor. He told me what to do. The other said, okay, she doesn't know. That doesn't seem like a great doctor. Although this audience seems not to agree very much with that. So let's see now what was the process behind. And this is to argue about that. So we didn't know the process. I didn't tell it to you on purpose. Dr. Imprecise really analyzed the data and couldn't find if it was A or B and decided to just say, I don't know. While Dr. Precise flipped a coin and came out A instead of B. So I'm pretty sure we don't need to do the hands now to say which one, which one you prefer. Yes, but anyway, I think the message here is just it's important to know the process. So it's important to know what is behind. It's not even about the uncertainty or imprecision. That's point number one that I would like to make. This point number two is more about the knowing how, when we don't know, right? So let's say you have 10 options, digits, and you have to guess the digits in an image. So you're giving the images. And there are three different approaches, okay? Which one is best? It's an approach that always predicts to you a digit, and given an image, it tells what is the digit in the image. It has an accuracy of 90%. Or let's take another approach that always predicts a digit for any given image with accuracy 99.9%, but it's allowed to say I don't know sometimes. So sometimes it says I don't know. I would say let's assume for now that the I don't know is not that often. Okay, we don't need to be too precise on that for the point I'm conveying. And third option here is an approach that sometimes predicts multiple options. Let's say it says a 6 or an 8 because the way that was drawn, but it's nothing else. And it has an accuracy of 99.99%. Accuracy here meaning the set contains the correct answer. Okay. Which one we prefer here? And again, I'm not going to do any hands, but it depends. It really depends on the situation, right? But it's, in my opinion, important to know when we don't know, when we have very risky scenarios. So if knowing that digit is that important, then maybe options 2 and 3 here are better than the option 1. Let's take another example. We have to consider uncertainty coming from many different situations, and Fabio in the morning already touched upon missing data. So in this example, BBC is paying us to discover the popularity of EastEnders. It's a soap opera show, and so we go there, and we decide to call 10 random numbers, okay, 10 random phone numbers. 4 people answer the phone and said that they like EastEnders. 1 person answered the phone and said they don't like EastEnders. 5 people did not answer the phone. So a typical approach is to assume missing data is missing at random, which would lead here to an 80% of the people like EastEnders. So is that meaningful? Are you okay with reporting that to BBC? I mean, I think BBC would be very happy, but is that something meaningful? Or even from the viewpoint of ethics, it's okay to report that. So that's my point, is beyond just being correct or wrong, but to be, you know, a good scientist, a good computer scientist, data scientist, machine learner. Is it okay to report 80%? And just as example, this is fake, right? This is a fake example, but standard is more popular among older people. This is not unknown. So we should know that. Young people much more often do not answer the phone these days. We also should know that. It's quite well known. I mean, I'm not saying that we should have dig into all this too much, but isn't those important information that might change how we interpret those 5 people who did not answer? And we should take that into account. We should really think about when we are doing inferences. So can we do more than the standard probability in this case would be standard, not just probability, but the standard inference people would just do missing at random and go with it. It's not good enough, right? At least I don't think it is. So we need, I think we need a better AI. So more properties, more interpretability, robustness, being cautious and being explainable and care about privacy and fairness. And this usually has benefits, but it does not come for free. So more computational resources, more intricate solutions that maybe are harder to maintain. There are many things that come with this. Are we willing to pay this price for this trustworthy AI? And it's a question I also have to myself. And I think the waters now are changing, and it seems that we are more and more willing to pay the price, but we are not fully there yet. This is a nice XKCG saying that, you know, you put something and you get something else, and then to improve, you just keep shaking your model. It's a way that we are doing many solutions nowadays. So maybe not a great way, but is a way. So I will quickly differentiate here 3 types of knowledge, and the thing is go way beyond that, and Fabio already gave you a way better view on this, so I'm simplifying things a lot. Let's say there's a football match between Italy and Sweden, and we are interested in the result for Italy, so if it's a win, a draw, or a loss. And I would say that there is determinism or certainty. For instance, the goalkeeper of Italy is just unbeatable. Buffon is just unbeatable. Bear with me. While Sweden always gets at least a goal, so no, Italy's taking no goal. Sweden always gets a goal, so which means that the probability of Italy winning is a certain win. Then there is uncertainty, which you could tell it as being, okay, win is 2 times more probable than draw, and draw is 3 times more probable than a loss, and then you can quantify this with a probability. But you could go beyond that and say, win is more probable than a draw, and this is more probable than a loss, but you don't say anything beyond that. And this is what I'm calling here imprecision, and you could quantify by a set of probability distributions. So in this example here, you have different degrees of certainty and uncertainty, but also different degrees of how much information you're giving and how much expressivity you have from one side to the other. Choosing one is related to your problem, right? And I'm going to argue here that there are cases that you can choose one or the other, but there are benefits on each one of them. So I will open a parenthesis here because I have to quickly explain to you a model that I'm going to use later on. But it's not really a big parenthesis because this is a model that models uncertainty, but uncertainty by using a probability distribution, okay, not sets of probability distributions. How does it work? Well, it's a model that is a circuit, just as a neural network is typically a circuit, so it does computations very efficiently. You can propagate numbers through it, but interpretability is a bit lost for the sake of computational being fast. In the end, this is a complex mixture of models. How it works? Well, it has 3 types of nodes in that graph. There are these leaf nodes, and in this example, I only use indicator functions. So it just sends you a signal if that's true or false, like a 1 and 0. For instance, if a variable is equal to a certain value. It has internal nodes of 2 types. Those are either weighted sums, and a weighted sum here you can really see just as a mixture model. So a weighted sum of the results of the children is the same as combining them as a mixture model. They have to be over the same variables. And you have a third type of node that's called the product node. This product node is the product of the children, but those children cannot have overlapping variables. So this is exactly independence, but it's a context-specific independence. It's an independence that holds there in that node, that the node might be in the network in a complicated place. So it doesn't mean that the variables are independent, but they are independent in that scenario, so in that subcase, okay? So this type of model, we usually draw in a graph, it's a DAG, and we do computations by propagating the numbers, by plugging number on the leaf nodes and propagating to the root, by doing what? Product is when is product, weighted sum is when is weighted sum. It's simple like that. And these represent a joint probability distribution. In this example, for two variables, A and B, both binary, assuming value true and false. And you can, with this model, compute likelihood, you can compute marginals, conditionals very efficiently. It's just a pass on this. So in linear time on the size of the model. So in this example, it's computing the P of A. We don't need to enter on details, but you just plug some specific things there, specific things on the leaf nodes, and you get marginals, for instance, efficiently from the model. So this type of model has many benefits, and I'm going to try to use them now in our continuation. But this is actually the parenthesis that I was going to make. So we found a relation between this type of model and decision trees and random forests. And I just want to mention to you, so this is sort of my advertisement of my own paper. We found a way of translating decision trees and random forests to that type of model, which is a probabilistic model. So this makes random forest become generative. The translation is actually quite simple. And with that, we keep the same results of random forests that exist. So state-of-the-art for tabular data, but typically even beyond with random forests. If you do machine learning, you probably are there too. Random forests are probably still the most used model in industry, and you gain a lot. So the treatment of missing data now is sound. You can do outlier detections very well. You can smooth the boundaries of the decision tree and adversarial training, sensitivity analysis, and so on. So this type of model, probabilistic circuits, have lots of power and can help us, for instance, to make models that already exist generative. So what is the advantage? So the first thing I want to sell here, being generative is great. Why? Well, you can use P of X. X here are the features, okay, and let's say that Y is what you want to predict. So when I say P of X, here is the P of the features that you have. It's not the conditional class if you would like to do classification. In this slide, what you have on the left are, we are using it for classification. On the left, you have the cases that have the worst P of X, like worst, in sense of lowest, meaning you saw samples similar to that less often. And on the right here, you have samples with high P of X. And the colors are whether you got right or wrong when you try to classify them. Okay, so you can see that on the left, you have way more reds, meaning that you made more mistakes when P of X was lower compared than when P of X is high, which is the right side. P of X can also be used to do outlier detections. You can use the P of X to say how likely this point is based on your training model, right? So in this slide, what I have is the wine data set, also very well known. And the comparison is that on top, we are using the P of Y given X. So we are looking to the probability of the class, posterior probability of the class for the example, and trying to use that to differentiate two types here, white and red. So we trained the model with one type of wine, and we only query with the other. So if you look here, you're going to see that the model can split the points way better when you look to the P of X than when you look to the P of Y given X. So being generative typically has benefits. Why that? Well, for instance, the naive-based classifier, which just as an example, tends to be very extreme. Like it either says, you know, this is red wine with 95%, I'm sure, or this is white wine with 95%. It's a typical situation with, for instance, the naive-based classifier. In this case, it's better to use the P of X probably than to use the conditional one. But the P of X has also limitations, right? So maybe not enough to just be generative there. So take back the example of numbers, and let's say 5 and 6 can be very similar. And let's say you have lots of 5 and 6 on your data. So you have plenty of mass in that area of 5 and 6, but they are all there together. So if you now look to P of X of one sample, it might be quite high because it is a 5 or a 6, but it does not help you to differentiate between 5 and 6. So looking to the P of X alone might not be enough indication of how well you're doing, so how much you are certain about what you are saying. And I would like to go then beyond that and to use sets of distributions. So Credal sets are going to be the type of technique I'm going to apply to the same model that we are already talking about. I will go a bit faster here because I think, well, not just you know, but Fabio already gave a nice introduction. So we are talking about a set of distributions. If you take a single one, you have a point here. If you take two different ones in blues, they are a point on the simplex. You have here a binary variable, so they are like two examples here. And if you take an interval, this is what I mean by a Credal set. In the Boolean case, it's just an interval. So the interval represents your knowledge and not just now one distribution. But as Fabio already mentioned, the things get more complicated if you go beyond binary, and then if you have different types of models there. If you want to go beyond binary, I have my example here with three options. It was the Italy versus Sweden case, so win, draw, loss. So your information in the precise case is represented by 1 point in the simplex. And your information, if you want to use a set, can be here a polytope on this. And this can have any shape. And I think that if you use very complicated shapes, then you fall outside the belief function thing that Fabio said. But if you use just intervals in certain way, then you are back. But that is the type of representation you can do with Credal sets. So you represent by a set of probability distributions. And how do we now represent here that we don't know? Well, in the precise case, we usually stuck a point in the middle. I mean, this is information. This is not a lack of information, right? So the uniform in the middle is not lack. It's a certain sort of indifference, but really lack of information would be to say it could be any P here. So use the whole simplex. But I assume you already sold on that from the morning. You can do more than that, right? You can use expert knowledge by saying win is more probable than a draw, and which is more probable than a loss. So you get a smaller set inside that. And you can even play with that and do better knowledge elicitation by mapping words to some intervals inside. Obviously, you may choose your way of mapping this, and some other person may have a different way of mapping this, but it gives you the freedom and specificity to do that, right, with those sets. You can go beyond a single variable and then have multivariate models. Of course, the polytope gets more and more complicated. In this example here, we have two binary variables, so the dimension now is 4, but we can represent in 3 dimensions by the fact that we know that they are not all the 4 independent because they are probability, right? So that helps us there. If you have multiple variables, then you also would like to deal with independence. So in the precise case, independence is a quite simple concept. We say that X and Y are independent if you multiply their marginals and you get the joint. That's okay, I'm being very quick here and simplifying, but basically you say that. In the imprecise case, on the sets, then it's not that simple because you have many. So which one has to be what here? Because you have many distributions. So there are 2 main concepts. One is called the strong independence. In this case, what you demand is that each one of the extremes of your set satisfies the stochastic precise independence. So for each extreme, if you multiply the marginals of that distribution, you have to get to the joint of that. And there is the other case, which is called epistemic irrelevance. And in this case, it is a concept based on sets. And this I'm mentioning here because it goes beyond in the spirit that Fabio was saying on what you want to represent in terms of knowledge. Is there a true distribution in there, or is just your knowledge is the set? In this case, Y is irrelevant to X, according to this distribution of X and Y, if the Credal set of X given Y is equal to the Credal set of X without given Y. This is an equality of set. Pay attention to this. When I have that equality, I mean the 2 sets have to be the same. Note that this is quite a different and more complicated concept to work with, because now you have to have some sort of way of comparing sets and working with the sets directly, instead of in the case in the middle that you can come back to the extremes and just do normal probability in each one of the extremes. So that's actually what we are going to do. So I'm mentioning that, but I'm going to keep using the strong case here. So back to the strong case. Indeed, you can do inferences with your set by just repeating the standard inference that you know how to do with all the extremes. I'm not saying this is efficient, but I'm just saying there is a mathematical way of doing which is sound. So if you want to marginalize, you marginalize each one of your extremes, and then you have a new set. If you want to do conditioning, you do conditioning in each one of your streams, and you have a new set. So if you want to combine them, you combine all your streams in every possible way, and then you have a new set. Usually you keep taking convex rule of that when you do those operations. So it's easy in the sense that it's the same operation we are used to do with probability. And with that, we're born already 25 years ago, what they call it Credal networks, which is the Bayesian network version with sets. So the graph has the kind of same interpretation with the conditional independencies, but each one of the nodes is associated to a set of distributions instead of to a single one. I'm not going to enter details because I'm not going to talk about Credal nets in the final part, but it's so to know that we have this type of formalism for making Bayesian networks become Credal using sets. And you have to use all the rules for combination and so on, and then you have a set of joint models from this model. And this is a quick example of it. So you put intervals and conditional intervals as you would do with conditional probabilities. Here you have conditional intervals instead of conditional values as you have in a Bayesian network. And this actually has been used by the Swiss Army for many years already. So there are people who care about these models that can give you more information about the results. So how we do the decision making with this, and I'm going to stick to the simple one, but you can then later take a look on the more complicated. If you have a set of models, one way of doing inference is then doing the inference with each one of the models, and you get a different result. And then you combine all those results. So in this example here, if you have you want to classify, so the probability of options, win, draw, and loss. What is the probability of win? It's not more of a number, but you can do the max probability of win and the minimum probability of win. By what? By taking every possible model that you have there inside. Let's forget about how hard it is to do that. There are quite efficient methods, but in many cases it's quite hard. I will not lie about that. But you get an interval in the end, and you can do the same for draw, and you can do the same for loss. How I take a decision now? Well, I could compare if the intervals overlap, and this is what this example is doing. So between win and draw, I will not really take a decision because the intervals overlap. So I will say, I don't know, could be win or could be draw, but it's not loss because the interval for loss, the max of it, is smaller than the minimum of the other, so it's never loss. So this is how you would do decision making for that. There are more sophisticated ways where you compare this pointwise on the probabilities. So the little bars there, this example is called maximality, but there are other criteria, and they are more precise as criteria. So they are more useful, but I will skip because of the time that we have. So in this case, you compare each one of the P's and you see if one dominates the other. In this case, even some intervals that overlap, you can still tell that one is better than the other because for every P, it's better than the other, and not just comparing the extremes of the intervals. So with that, I got to my final model, which is my Credal sum product network. I take the weights of those mixtures of the sum nodes, and I put Credal sets there. And that's it. We have now a Credal model, and this Credal model can be used to do classification by comparing the intervals as a criteria. So sometimes the model will not be able to say if it is win or draw. It will be undecided. Sometimes it will be decided. You say it's a win, depending on the sample that you give to the model and the inference you get the intervals for that inference. So what we have done extensively already is to generate a Credal model from a precise model by attacking the parameters. So I first learn a precise model, and then I do a perturbation of the parameters to create the set. It's called epsilon contamination of the parameters, and this generates a little set around the parameters. And what is very interesting is that we can use this as a measure of robustness. How? Well, generate a little set with a certain epsilon. Now, run inferences and check if you have more than one output in the end, like the intervals overlap. Do they overlap? Reduce the epsilon. They don't overlap, increase your epsilon and repeat. At some point you get to an epsilon that is the borderline up to the point that the result does not change. It's always that single one, because you kept doing this, trying to find what is the largest epsilon, such that for every model inside your model, you answer the same answer and a single one. And that's a nice way of doing epsilon robustness. So you get to graphs like this, which are pretty nice graphs. So from the left to the right, it's showing the model and on the X, it tells how much the model is confident about the output is given, and on the Y is the accuracy of the model. So, and this is done by chunks, right? So of the data, so as the model is more confident, it also has more accuracy. So that's what the graph is telling us. We don't have to enter on the details, but it's nice that it's quite monotone on this data set. So as the model is more confident, the model also does better. So this epsilon robustness, by the way, is not a property of the model, but of every instance. When you give an instance to the model, you compute the epsilon of that instance, and then you know if you are confident or not on that classification. Here we just aggregated them in a graph to tell you the final accuracy. And then you get a different graph as before, but instead of P of X, I'm using the epsilon robustness. And this is what you see here on the left. On the right is the same as before, but on the left you have the new version. Is this better or worse than P of X? Well, in experiments, actually is a bit better, but it's not just about being better. Look at the type of results you get. They are way more heterogeneous, while in the left, it's all ones. And on the right, no, it's related to something that is not just how many points you saw on that. So you already give an impression here by looking, you have so many ones there that the P of X is doing something else. It's not really just how it knows about that model. And I know that I'm already over time. Let's just see two more results, and I'm okay yet? Okay. So I have two more examples doing similar things. So this is still with digits, but it's just to show you some statistics about this epsilon robustness. So in the table here, you have the yes. Of course. Yes, we have already done that, and it does a very similar job. So it depends on the data set you have. You are going to do a better job using the standard approaches or using this. And my conjecture, because this is quite experimental, my conjecture is that this is related exactly to the example of before when I said if you have lots of 5s and 6s that are close or mixed, then one is going to do better than the other. But if you don't, then the precise will do better because the P of X is meaningful. But then there are cases when it's not. And we're still trying to find exactly the sweet spot on that. So, but we can discuss more on that topic. I think it's a very valid one on how well this works and in which situations. So this is just a little bit of statistics about the numbers. So on the left side where you see CSPN, what you have is that is the statistics for when you are right, and the statistic is on when you are wrong. So you see that the median of correct is much larger. So the robustness that the model think that it has, or how much the model trusts itself, which is I'm calling absolute robustness here, is much higher. You can even see that the maximum when it's wrong is just around 0.1. That's the maximum robustness of any instance when the model was wrong. While the median when it was correct is already 0.03. So there is a bit of overlap, but it is clear that it can knows a bit more when it's right and it's wrong before checking, right? The model has this information. We are not using the output to compute it. So it's nice that the model can know this without knowing the label. On the left side of this table, what you have is a quick comparison we did with the posterior P of the class and comparing the highest minus the second highest. And it doesn't work that, but it's known that this is quite unstable. It's still very much used, but it's way more unstable if you try to measure how well you're doing by just measuring how high is your P of Y given X. As I had already argued before for the naive classifier, for instance, and also holds for others. And this is a work already for long ago, but I still think it's nice to show the fact that the model had more trouble to identify the motions on faces that are more similar to each other than those that are more forced and different. So in this case here, what we have on the table, and I will try to read with you, is that the model was way more confident with surprise, because look at the faces of surprise, how they are forced there compared to the other ones. So it also matches here in some sense with what we would expect on where the model is more confident and when the model is less confident, when there is more room for interpretation, what is one thing or another. And my very final topic that I want to mention, because this is very recent and we are doing right now, we are mixing data with probabilistic propositional logic assessments, and we are putting this inside this type of model. And how we do this? By using Credal sets, for instance. So in this example here, let's say that you tell me that the P of A or B is equal to X, a value, number, okay? I can plug this on the weight there, of the weight of A or B, and I can leave open, so leave as vacuous, the weights of the possible atoms of that. I don't tell where it should go, I just leave as Credal that. And by that I mean the weights for A and B, A not B, and not BA. I leave that vacuous, so it's going to be distributed somehow when I do inferences, but it's basically I'm putting in the model only the information that I have, which is the probability of A or B, but nothing more than that. So this is a recent way of trying to combine logics and machine learning models, because, well, these probability circuits can be learned from data in multiple different ways. And these Credal models have been connected to causal inference and identifiability in a very nice way. This is a slide is by Alessandro, so when it's written here, joint work, is by Alessandro Antonucci, not by myself. I really stole the slide, but I'm making a reference to him. Hi, Alessandro. When you see this later. This is an ongoing research, but it's really showing, for me, an opening door for causal inferences where, in cases where you don't have identifiability, you can still continue doing causal inference. And I will leave it like that, but it's kind of like opening doors for causal machine learning, and I think there is an opportunity for jumping in or even doing more stuff on top of that. And we have many other ongoing researches, my very last slide. So we are using Credal models, starting to use Credal models for causal inference in view of that. We are using Credal SPNs for portfolio optimization. So we use that to quantify the uncertainty of the return of certain investments to build a portfolio. We are doing Credal clustering to learn these models in a more robust way. By Credal clustering, it's kind of a soft version, but even more on belief functions actually direction. I think belief functions are perfect for a sort of Credal clustering, or you can call evidential clustering if you would prefer. And we are using the Credal sets to combine logic and deep learning models. And with that, I conclude, and thanks a lot, and sorry for being a bit late on time.
Any questions from anyone?
Thanks for that presentation. Maybe a naive question on the absolute robustness. So we're presenting this specifically for Credal sets, or could this apply to any model within Sketch?
I could also yell, I guess. Maybe it's a bit more efficient. So thanks for the question. What we are doing now, so the way we create the epsilon robustness is mostly through epsilon contamination, which means is specific for this type of way you do the contamination, but you could do in different ways. So right now what we do is that we really start with a precise model and then we expand the parameters around that parameter. This could be used for any model, the way of expanding. Then obviously you must have algorithms to compute the marginal distribution or actually a conditional distribution of the class, for instance, given the features in case you want to do classification. The advantage of using Credal probabilistic circuits is that, and actually I didn't mention that, we can compute intervals, we can compute maximality, the decision criteria, everything is still in linear time on the size of the model. So we can still propagate just once on that thing, actually twice sometimes, but it's still linear on the size of the model. So our, let's say, bottleneck is, can you compute posterior probabilities or not? If you can, then you can do with any model. And there are some models that is very hard to compute these intervals well. For these models, you can compute very efficiently. Some others you might need to approximate, like the Credal networks that I mentioned. We don't know how to compute the maximum probability of a y given x for any kind of combinations of y and x. For instance, if you have missing data or partial observations, we don't know how to do that efficiently. We can approximate very well, but we don't compute those bounds efficiently in a theoretical tractable way.
Can I apply the same thinking to the standard neural network? Say you just have a network and it has one of those parameters, and I might have an image coming in that gives some class prediction, and I could also permute those all parameters and see some metric if the class predictions change. And do this epsilon trick of sort of zooming in, how much do I need to fizzle with all the parameters to see how it affects it, right? So the idea is more generic, you know?
Okay.
The benefit of your approach and your modeling, this is one of the evaluations.
Yeah, so thanks for that. So indeed, so the question is, can I do the epsilon contamination or other type of perturbation on a neural net, right? Or other models. So the difference that would happen is the following. So here, each one of the extremes of this epsilon contamination has a probabilistic interpretation that is a probability distribution. When I look to that set, that is a Credal set. So I'm bringing on my, in my belt, all the theory of probability with me. If I do that for a neural network, and of course you can perturb those intervals, right? You don't have that. So I would not have that. And that's what I would be missing. So what is the meaning now of that perturbation? So the difference here is that the epsilon that I showed, that I call it epsilon robustness, actually we can translate to something to some extent interpretable. What is the meaning of that epsilon? It's a measure of how far you are from a point to the whole simplex. So it's really probabilistic, the interpretation of that epsilon. On the neural net, we would lose that, but we could do it. But by losing the interpretation, it also becomes harder. And in the case of neural networks, because you may have negative parameters, it may be that this is not even like consistent somehow on how you do. So I would have to think more on how to do that. I could tell you that if everything is positive, then I think we still have an interpretation for that, but it's known that positive neural nets are a subcase of neural nets. It still works in some domains, but not in others. The main problem is actually not even, let's say, if you do ReLU or some other activation you put there, you can still have some sort of probabilistic interpretation, even of nodes in the middle. It's just, it's a bit dirtier interpretation than in these circuits, but you can. But then the negative values create the same sort of situation and difficulty you have when you perturb parameters of a Markov random field, which, by the way, it's a simplistic, one of the precursors, I would say, even of neural nets in some sense. So if you perturb this in a model that is not normalized, or energy-based models and so on, the interpretation of this perturbation is lost. And so we have to take lots of care. So does that really make sense or not? Sorry for a bit long answer on that.
We're also looking at generative AI from robots. And earlier, so one thing that is there is measures of diversity of the output. So I was wondering whether you have used any metrics of diversity of your generated output, like in the slide you showed before, just as whether a method is better.
Okay, so the question is whether we have used any type of diversity measure about the output to quantify how good it is. Yes. Yeah, so the question is about this diversity that you see on this slide that I mentioned when we went through the slide. And I'm taking a bit of time here to say that the answer is no. We have not done that. And it would be a very nice thing to do. We did that, let's say, partially, because we did this analysis, for instance, in the case of digits for different digits, based by mixing only a few digits in different ways, and then you can see how some of them are react to the others, because when you have fewer, then you can just by the measures we are using, measure also the diversity when you reduce the amount. So you know how skewed you are in the direction of one or another, but we have not done that properly yet. And I think it's an open thing and good thing to do.
Thank you for this presentation. The question is that because that we have linked data, noise data, so we have a process representation over the base equivalence. I'm wondering if we have infinite data of the student, could equivalence could be reduced to a single probability, or it can be. I have this question, yeah.
Thank you. So the question is, you have a Credal set, so you have many distributions. If I keep you giving more data and more data, more data, is this converging to a singleton? So. And then you have a good point. I did not tell here how to learn a Credal model except for doing epsilon contamination. And in the epsilon contamination, actually, I'm controlling the size of the model by choosing the epsilon. So it's not so pertinent on there. But now let's get to your point, which is very nice. So there are different interpretations and different ways to learn, depending on how you interpret the model and depending on how you learn. So if you take the simplest way of learning an imprecise Credal set, I would say imprecise Dirichlet model, which is a mapping of the Dirichlet, well, the Dirichlet multinomial conjugacy, but applied to the imprecise case. In that case, you put the imprecision on the priors. If you fix the amount of priors, so you decompose the prior on the strength and the locality, and usually you keep the strength fixed and the locality you allow to vary. Because you fix the strength of the prior, if you give me infinite data, that learning procedure will converge to a point. So eventually the interval gets smaller and smaller, but that is a property of that learning approach that have been used in that case, right? I can tell you an example where you do not converge to a point. Assume a case where you do not assume MAR. So you say missing data might be against me. I'm not ignoring it. And now if I keep you giving more data, but this data always have some parts that are missing, you would not converge to a single point. Because as you get more data, you also get more noise. Noise in this case, more lack of information of the missing data, and you have to treat this properly. You cannot just ignore it. So it depends on your learning procedure, but it's a very good point. And that also is a crucial point on this methodology and behind. People are still debating, are there really Credal models, or they are always a lack of information of a precise model that is underneath this? And I think is open for debate.
Yeah, conscious of time, so actually this is the last one. Additional question is, we are talking, I'm working on neural networks. So if also Fabio talk today is like we have 7 order distribution of distribution which Bayesian treat it in your network way. So I also find a Credal net. It's like a static distribution. Do you have some intuition like so how could we finally compare these two kinds of modeling? So we have a distribution over distribution from Bayesian side, and we also have Credal set like a static distribution. So I also ask myself or question myself if there are proper way to model from one to another, or if we find a platform that we can compare fairly. You have some intuition. Thank you.
Okay. Thanks for the question. So the question is, how do I compare well a hierarchical Bayesian model, so maybe priors on priors or Bayesian neural nets with a Credal version of that, right? And for the sake of time, because the answer here is going to go all over our next commitments in the agenda, I will answer to you the following. Hierarchical Bayesian model is a Bayesian model, so it's still one distribution there. It might be a very complex one, but you are choosing how much you weight the different parts of the information you have, even if you do that hierarchically. While the Credal model is a set of models, so it's really like a combination of different probability distributions where you are not weighting how you pick each one of them. You have to decide on how you're going to use. You can use that as I'll take max, I'll take mean, max, mean. I will compare them in a certain way, like with the decision criteria that we quickly discussed here. But you have a set of competing things, and you have to decide how to work with the set. The hierarchical version, you actually weight how you pick them, and then that somehow collapses still to a model again. It's a very sophisticated and is actually impressive results in many cases, but I would still say that that belongs to the precise probability. Now, how to compare? We continue later, because either the answer is very long or I don't have it. So it's one of those two, but we have to discuss a bit more.
Okay, so any other burning questions now? We are into the uncertainty of what our roadmap session so yeah. So I think the current proposal is that we'll have 3 breakout sessions. We have a new proposal.
So my proposal is that